A function is effective computable by a physical system if and only if it is Turing machine compatible. This is the Church-Turing thesis. The Turing machine provides an atomic computing element. The action of a Turing machine is determined completely by 1, the current state of the machine, 2, the symbol in the cell currently being scanned, and 3, a table of transition rules which serve as the program for the machine. According to Eberbach, Wegner, and Goldin, Turing machines do not model all computations. The TM is a closed world model, and dynamic changes in the world outside the TM has no bearing on the computation itself. The TM's computation is completely predetermined by its input, which has to be defined in advance. It cannot be altered from the outside once the computation begins. TMs compute functions from these inputs to some output. Once the output's value has been determined, the computation stops. They cite the example of the operating system conundrum to make their point. They cite the operating system conundrum as an example. The operating system does not provide useful computations by itself, except managing other Turing machines that provide useful computation. The operating system is a Turing machine that allows computing resources to be shared by multiple Turing machines, in this case, processes, threads, etc. In this model, with an operating system, a process is a Turing machine that provides the desired computation whose resources are controlled by the operating system. For example, if two processes are sharing the same resources, the operating system then allocates the resources by time slicing them and giving them to both processes based on policies that are externally determined. In short, the fault configuration, accounting, performance, and security management is performed by the operating system, and the operating system provides a set of Turing machines the resources that are required to perform their computations. We transform the Turing machine implementing von Neumann computing into a distributed intelligent managed element which implements the non-von Neumann managed Turing machine. The control network is an overlay over the current von Neumann serial computing network. Each Linux process is then controlled by the FCAPS management, and essentially we convert every Linux process into a managed computing element that provides fault configuration, accounting, performance, and security management. The control network allows to set up the various parameters that are required for executing the process, and it can start by loading and executing the process executable. The control network also allows you to stop the computing machine at any time you desire based on policies, and you can also restart, for example. So this picture shows a simple service being controlled, loaded, and executed. This picture shows the implementation of the DIME networks using a parallax bare metal operating system, in which the operating system essentially sets up each core into a distributed intelligent managed element, sets up the control, and allows the execution of the Turing machines in each core. This picture shows the loading and executing of various programs in each DIME. The Turing machine providing computation is managed locally and also globally using the signaling control architecture. The self-management of each computing node and the signaling capability allows a network of DIMEs to be composed into executing managed workflows. Thank you.